Let's start lecture number 17 of CS317 Operating Systems. Our discussion on concurrency continues. We use the William Stallings book and refer to chapter 5 of this book. In the previous lecture, we explored inter-process communication using message passing. We learned how to use messages to enforce mutual exclusion. We learned how to use messages to solve the producer-consumer problem. We explored the readers-writers problem and saw one solution where readers were given priority. Some synchronization problems have been designated as classical synchronization problems because of their educational value and because we find many real-world problems that can map to them. So the solution of the classical synchronization problems can be used as a solution for real-world problems that resemble them. We are focusing on a very special classical synchronization problem called the readers-writers problem. Previously, we focused on a solution to the readers-writers problem where readers had priority. Now we look at another solution to the readers-writers problem. This solution guarantees that no new readers are allowed access to the data area once at least one writer has declared a desire to write. So this is a solution to the readers-writers problem where writers have priority, and we are using semaphores here for synchronization. However, figure 5.23 has some errors in code, which I would like to point out. The semaphores have not been initialized. All of them must be globally defined and initialized to 1. The third last line of code in the writer process should be write count minus minus. In the original figure, it is only write count. I have corrected the figures in this video. Please correct the code in your book. For writers, the following semaphores and variables are added to the ones already defined. A semaphore RSEM that inhibits all readers while there is at least one writer desiring access to the data area. A variable write count that controls the setting of RSEM. A semaphore Y that controls the updating of write count. For readers, one additional semaphore is needed. A long queue must not be allowed to build up on RSEM. Otherwise, writers will not be able to jump the queue. Therefore, only one reader is allowed to queue on RSEM, with any additional readers queuing on semaphore Z immediately before waiting on RSEM. You can see that the code has a lot of semaphores. And to understand it, I need a prop. So the best prop that I can think of is a parallel trace. I understand that this parallel trace is a long one, but through it I will be able to demonstrate all the complexities of the code, and I hope that you will understand it better. When we start, all semaphores are 1. We have two counting variables, read count and write count, which are keeping track of the readers and the writers in the system. We do not have any readers or writers in the system right now, so both read count and write count are 0. Writer 1 comes into the system. It issues a wait on y becomes 0. It increments write count becomes 1. It issues a wait on RSEM becomes 0. It issues a signal on y goes back to 1. It issues a wait on WSIM becomes 0, and then it starts writing on the file. Reader 1 comes into the system, issues a wait on Z becomes 0. Issues a wait on RSIM becomes -1. Reader 1 is blocked in the queue of RSIM. Writer 1 is writing on the file. Reader 1 is in the queue of RSIM. Reader 2 comes into the system, does a wait on Z. Z becomes -1. Reader 2 blocks in the queue of Z. Writer 1 is writing on the file. Reader 1 is waiting in the queue of RSIM. Reader 2 is waiting in the queue of Z. Writer 2 comes into the system, issues a wait on Y. Y becomes 0. Increments write count becomes 2. Issues a signal on Y. Y goes back to 1. Issues a wait on WSIM. WSIM becomes -1. Writer 2 blocks on WSIM. Writer 1 is writing. Reader 1 is in the queue of RSIM. Reader 2 is in the queue of Z. Writer 2 is in the queue of WSIM. Reader 3 comes into the system, does a wait on Z. Z becomes -2. Reader 3 blocks in the queue of Z behind R2. When writer 1 finishes writing, it issues a signal on WSIM. WSIM becomes 0 and writer 2 unblocks. So the system is in this state now. Reader 1 is blocked in the queue of RSIM. Readers 2 and 3 are blocked in the queue of Z. Readers have come into the system, but so far they have not registered themselves. So read count is 0. It has not been incremented so far. Write count is 2. W1 has just finished writing and W2 has just been unblocked. Writer 2 starts writing on the file. Writer 1 issues a wait on Y. Y becomes 0. Decrements write count becomes 1. Signals on Y. Y becomes 1. Writer 1 leaves the system. Writer 2, which was writing on the file, completes writing and does a SIM signal on WSIM. WSIM becomes 1. Issues a wait on Y. Y becomes 0. Decrements write count becomes 0. It signals on RSIM. RSIM becomes 0 and reader 1 unblocks from the queue of RSIM. Finally, writer 2 signals on Y. Y becomes 1. Writer 2 leaves. So both writers have left now. Reader 1 has just been unblocked. Reader 1 does a wait on X. X becomes 0. Then it increments read count. Read count is 1. Issues a wait on WSIM. WSIM becomes 0. Then it signals on X. X goes back to 1. Then it signals on RSIM. And RSIM goes back to 1, 2. So the system is like this. Readers 2 and 3 are blocked in the queue of Z. Read count is 1. Write count is 0. Reader 1 issues a signal on Z. Z becomes -1. Reader 2 unblocks. Reader 1 goes on to read the file. Suppose a new process comes into the system. This is a writer process. We call it writer 3. It issues a wait on Y. Y becomes 0. It increments write count becomes 1. It issues a wait on RSIM. RSIM becomes 0. It issues a signal on Y. Y goes back to 1. It issues a wait on WSIM and WSIM becomes -1. Writer 3 is blocked in the queue of WSIM. Why did this happen? This happened because right now we have readers in the system and reader 1 is reading the file. As long as readers do not exit the system, writers cannot come in. Reader 2 does a wait on RSIM. RSIM goes to -1. Reader 2 blocks in the queue of RSIM. Why did this happen? Right now reader 1 is reading the file. A writer has just come in. Reader 2 came before this writer, but remember that this system prioritizes writers. So now when it knows that a writer is waiting, it will not allow another reader to go and access the file. It will block any pending readers, clear off the current reader, and then invite pending writers to come and write on the file. Reader 1 does a wait on X, X becomes 0. It decrements read count becomes 0. It issues a signal on WSIM, WSIM becomes 0 and writer 3 unblocks. Finally, reader 1 does a signal on X, X goes back to 1 and reader 1 leaves the system. Who is active in the system now? Writer 3. Writer 3 starts writing on the file. When it has finished writing, it issues a signal on WSIM and WSIM goes back to 1. Now the system is like this. Reader 2 is blocked in the queue of RSIM. Reader 3 is blocked in the queue of Z. Read count is 0. Write count is 1. Writer 3 does a sim wait on Y becomes 0. It decrements write count becomes 0. It does a signal on RSIM becomes 0 and reader 2 unblocks. Writer 3 does a signal on Y goes back to 1. Writer 3 leaves the system. Who is active in the system now? Reader 2. Reader 2 issues a wait on X becomes 0. Then it increments read count goes to 1. Then it issues a wait on WSIM becomes 0. Then it issues a signal on X becomes 1. Then it issues a signal on RSIM becomes 1. Then it issues a signal on Z becomes 0. Reader 3 unblocks. Reader 2 starts reading the file. Meanwhile, reader 3 does a sim wait on RSIM becomes 0. Then a sim wait on X becomes 0. Then it increments read count becomes 2. The system is currently like this. There is no process blocked in any of the queues. There are 2 readers and no writers. Reader 3 does a sim signal on X goes back to 1. It does a sim signal on RSIM goes back to 1. It does a sim signal on Z goes back to 1. It starts reading the file. When it finishes reading, it does a wait on X goes to 0. It decrements read count becomes 1. It signals on X becomes 1 and reader 3 leaves the system. The last person to leave is reader 2. It does a wait on X becomes 0. It decrements read count becomes 0. It does a signal on WSIM becomes 1. Then it issues a signal on X becomes 1. Reader 2 leaves. When everybody has left the system, all semaphores go back to 1. All counting variables go back to 0. This table summarizes the states of the queues for the code that we just saw. When only readers are present in the system, The first reader sets WSIM to 0. Then it starts reading. Readers keep coming in and reading. When the last reader leaves, it sets WSIM back to 1. When the system has only readers, no queues need to be formed, as they can all read together. When only writers are there in the system, the first writer sets RSIM to 0. Then it sets WSIM to 0 and starts writing. As another writer comes in, it waits on WSIM. All writers wait in the queue of WSIM. When the last writer leaves, it sets RSIM back to 1. Suppose readers and writers are present in the system, but a reader has come first. So the reader sets WSIM to 0 to stop writers from coming in while it reads. Any writer after the first reader sets RSIM to 0. The second reader to come into the system waits on RSIM. All other readers wait on Z. All writers wait on WSIM. When the first reader finishes reading, the writers are allowed to write mutually exclusively. The last writer unblocks the reader on RSIM. This unblocked reader invites all readers queued in Z to come read with it. Suppose readers and writers are present in the system, but a writer has come first. So the writer sets WSIM to 0 to stop writers from coming in while it reads. The writer also sets RSIM to 0. The first reader to come into the system waits on RSIM. All other readers wait on Z. All writers wait on WSIM. When the first writer finishes writing, the writers are allowed to write mutually exclusively. The last writer unblocks the reader on RSIM. This unblocked reader invites all readers queued in Z to come read with it. An alternative solution which gives writers priority and which is implemented using message passing is given in figure 5.24. This figure has a lot of coding errors, so please do not refer to it. Use the code that I use here instead. When a reader I wants to read, it places its ID I in a message called R message and sends it to the controller's read request mailbox. Then it blocks on receiving a message from the controller in its own mailbox, rbox I. After it has received this message, it starts reading the file. When it finishes reading, it places its ID in a message called rmessage and sends it to the controller's mailbox called finished. This is how the reader process works. Let us now look at the writer process. When a writer J wants to write, it places its ID J in a message called wMessage and sends it to the controller's write request mailbox. Then it blocks on receiving a message from the controller in its own mailbox wbox J. After it has received this message, it starts writing the file. When it has finished writing, it places its ID in a message called wMessage and sends it to the controller's mailbox called finished. There is a controller process that has access to the shared data area. The controller is equipped with three mailboxes: read request, write request, and finished. That is one mailbox for each type of message that it may receive. The controller process services write request messages before read request messages to give writers priority. In addition, mutual exclusion must be enforced. To do this, the variable count is used, which is initialized to some number greater than the maximum possible number of readers. In this example, we use a value of 100. The actions of the controller can be summarized as follows. If count is greater than 0, the controller checks all its mailboxes in this sequence. First finished, then write request, then read request. If finished mailbox has a pending message, the controller receives it and increments count. Count remains greater than 0 and the controller keeps receiving finished messages and incrementing count until finished mailbox becomes empty. If finished is empty and write request has a pending message, the controller receives it and subtracts 100 from count. Remember that we started with count equals to 100. So this means if a writer comes into the system, count becomes 0. If both finished and write request are empty, but read request has a pending message, the controller receives it, sends an OK message to this reader's mailbox, and decrements count. When count is greater than 0, the controller services all finished messages first. Then it services write requests and then read requests. If count is equal to 0, then the only request outstanding is a write request. The controller sends an OK message to the writer's mailbox, W box, and blocks to receive a finished message. During this time, as the controller does nothing, mutual exclusion is enforced. When the writer's finished message is received, controller sets count back to 100. If count is less than 0, then a writer has made a request because of which count became 0 and readers are also present due to which count became less than 0. This means that the requesting writer is waiting for active readers to move out. The controller blocks to receive finished messages which would come from any one of the readers, and when it receives it, it decrements count. As long as readers remain in the system, count is less than 0 and the controller blocks to receive finished messages from them repeatedly. When all of the readers leave, count becomes equal to 0. Then the controller sends an OK message to the writer's mailbox W box and blocks to receive a finished message. Now we do a parallel trace of the code that we just saw. When we begin our trace, all mailboxes are empty and count is 100. All receives are blocking receives. All sends are non-blocking sends. Keep that in mind. Writer 1 comes into the system. It puts its ID in a message and sends it to the write request mailbox. Then it blocks to receive a message from the controller in its mailbox wbox1. Since count is greater than 0, the controller starts checking mailboxes. Finished is empty, so it proceeds to write request. The controller receives the write request by writer 1, subtracts 100 from count, count becomes 0. So the controller sends an OK message to wbox1 and blocks to receive a message in the finished mailbox. Writer 1 receives the controller's OK message and starts writing on the file. Reader 1 comes into the system. It puts its ID in a message and sends the message to the read request mailbox. Then it blocks to receive a message from the controller in its mailbox rbox1. Writer 2 comes into the system. It puts its ID in a message and sends the message to write request mailbox. Then it blocks to receive a message from the controller in its mailbox wbox2. Reader 2 comes into the system. It puts its ID in a message and sends the message to read request mailbox. Then it blocks to receive a message from the controller in its mailbox rbox 2. Writer 1 completes writing. It puts its ID in a message and sends the message to the finished mailbox. All this time, the controller had been blocked. The message from writer 1 in the finished mailbox unblocks the controller, which sets count back to 100. So far, finished mailbox is empty. Write request mailbox has one message from writer 2 and read request mailbox has two messages from reader 1 and reader 2 and count is 100. W1 or writer 1 has left. Reader 1, reader 2 and writer 2 are waiting. Since count is greater than 0, the controller starts checking mailboxes. Finished is empty, so it proceeds to write request. The controller receives the write request by writer 2, subtracts 100 from count. Count becomes 0. So the controller sends an OK message to wbox 2 and blocks to receive a message in the finished mailbox. Writer 2 receives the controller's OK message and starts writing on the file. Then it completes writing. It puts its ID in a message and sends the message to the finished mailbox. All this time, the controller had been blocked. The message from writer 2 in the finished mailbox unblocks the controller, which sets count back to 100. Since count is greater than 0, the controller starts checking mailboxes. Finished is empty, so it proceeds to write request. Write request is empty, so it proceeds to read request. The controller receives the read request by reader 1. The controller sends an OK message to rbox 1 and subtracts 1 from count. Count becomes 99. Reader 1 receives the controller's OK message and starts reading the file. Since count is greater than 0, the controller starts checking mailboxes. Finished is empty, so it proceeds to write request. Write request is empty, so it proceeds to read request. The controller receives the read request by reader 2. The controller sends an OK message to rbox 2 and subtracts 1 from count. Count becomes 98. Reader 2 receives the controller's OK message and starts reading the file. Writer 3 comes into the system. It puts its ID in a message and sends the message to the write request mailbox. Then it blocks to receive a message from the controller in its mailbox wbox 3. So far, the finished mailbox is empty. Write request mailbox has one message from writer 3 and read request mailbox is empty. Count is 98. Writer 1 and writer 2 have left. Reader 1 and reader 2 are reading. Writer 3 is waiting. Since count is greater than 0, the controller starts checking mailboxes. Finished is empty, so it proceeds to write request. The controller receives the write request by writer 3. The controller subtracts 100 from count. Count becomes -2. Since count is less than 0, the controller moves into the while loop and blocks to receive a message in the finished mailbox. Reader 2 completes reading first. It puts its ID in a message and sends the message to the finished mailbox. All this time, the controller had been blocked. The message from reader 2 in the finished mailbox unblocks the controller, which increments count. Count is now -1. Since count is less than 0, the controller moves into the while loop and blocks to receive a message in the finished mailbox. Reader 1 completes reading next. It puts its ID in a message and sends the message to the finished mailbox. All this time, the controller had been blocked. The message from reader 1 in the finished mailbox unblocks the controller, which increments count. Count is now 0. So the controller sends an OK message to W box 3 and blocks to receive a message in the finished mailbox. Writer 3 receives the controller's OK message and starts writing on the file. Writer 3 completes writing. It puts its ID in a message and sends it to the finished mailbox. All this time, the controller had been blocked. The message from writer 3 in the finished mailbox unblocks the controller, which sets count back to 100. Since count is greater than 0, the controller starts checking mailboxes. All mailboxes are empty. Throughout this trace, you must have noticed that we always serve the writers first and that the writers access the file mutually exclusively. Let's do an analysis of the message passing solution to readers writers problem. The technique is simple and flexible in many ways. Any number of readers can be accommodated. The variable count can be set to the maximum number of readers plus 1. In our example, the maximum number of readers that could be accommodated was 99, and hence we initialized the variable count to 100. If the sequence in which the controller checks mailboxes is changed in the body of if count is greater than 0, the same code can be made to prioritize readers. If you remember, when the controller was checking mailboxes, it went in a certain sequence. First, it checked the finished mailbox, then the write request mailbox, then the read request mailbox. When the controller checks write request first, writers are prioritized. But when it checks read request first, readers are prioritized. So what I am trying to say is if the controller first checked finished, then the read request mailbox, then the write request mailbox, you would have the same code, but then you would be prioritizing readers. When we want to enforce mutual exclusion, we make the controller send an OK message to a writer, and then we make it issue a blocking receive for a finished message from the writer. The blocking receive blocks the controller and nobody else can be issued an OK message. This is such a simple technique to enforce mutual exclusion. Block the person who would grant access. Now I am going to leave you with some homework. Draw a parallel execution traces using the following conditions. Make assumptions that you deem necessary as you go along. So every one of you will make different assumptions and that's totally okay. I just want you to exercise parallel traces. So the first homework is use the semaphore solution to readers writers problem. Writers have priority with 3 writers and 2 readers. The order of arrival of the processes are reader 1, writer 2, reader 2 and writer 3. The second question is use the message passing solution to readers writers problem. Writers have priority with 3 writers and 2 readers. The order of arrival of the processes are reader 1, writer 2, reader 2 and writer 3. I have done enough parallel traces with you and I am sure that you will be able to draw these parallel traces up. They will be lengthy but they will be fun. The things that we learned today. We explored the reader's writer's problem and its various solutions. We realized that both the semaphore approach and the message passing approach are equally effective in solving classical synchronization problems. We learned how to do dry runs of long parallelly executing processes. As always, my dear students, I conclude on the same points. Read the book, Do the homework. Don't leave it because I didn't ask you to submit it. That should not make any difference. You should do everything that I assign to you, because it is not only going to help you understand the course and the topic better, it will help you in your final paper as well. Write your questions on a piece of paper and keep it in front of you during the online session. If you have suggestions relevant to content or quality of this lecture, email them to me. I'll see you in the next online session, and we'll talk about the lectures that would be relevant to it. Take care of yourself. Allah Hafiz.